In this video, I want to have a look at maximum and minimum problems. So we can use calculus to help us solve problems that involve maximization and minimization. And sometimes we'll be given an equation that represents the situation to use. If not, though, we're going to have to come up with that ourselves before we can use our calculus skills. So the problem that we're going to have a look at says a rectangular field is going to be fenced, and then it's going to be divided into 6 smaller rectangles like it's shown in this picture here. So we're going to fence all the way around the outside of our field, and then we're going to have 2 fences going this way and 1 long fence going along here to split it into those 6 smaller fields. It says that the total length of the fencing that we have available is 120 metres, and we want to find the maximum possible area, that should just say area, not areas, of that big field. So we don't have any variables or anything there. We're not given an equation, so we're going to have to make it. So let's call this length here, that whole length along there, let's call that x, and let's call this whole length along here, let's call that y. So first off, we know that the fencing that we have available is 120 metres. So that 120 metres is going to be needed to use in all of that fencing. So we're going to have 4 sections of fence that are x units long, plus we're going to have 3 sections of fence that are y units long. So that 120 is going to be 4x plus 3y. So that's looking at the amount of fencing that we have. But the question actually asks about the area. Now the area of that whole big field would just be x times y. So we have 2 equations now, but we've got x's and y's in both of them, and it's getting a bit messy, and it's not going to help us. So what we're going to do is we're going to rearrange this first equation to get y as the subject, and then we're going to substitute it into our second one. So rearranging this, we would subtract 4x from both sides, equals 3y, and then we would have to divide everything by 3. So I'm also going to bring the y over the other side. Then 120 divided by 3 would be 40, and we'll leave this as minus 4 over 3x. Now we're going to substitute this up into here. So we're going to have x outside of 40 minus 4 over 3x, and we can expand that out. So we'd have 40x minus 4 over 3x squared. So this equation here, this function, represents the area of this whole field based on what we make the width. So what we can do if we want to maximize the area is we're going to differentiate this function and find the maximum. So differentiating that function, we would have 40 minus 8 over 3x. Now to find where the maximum point is, we want to find the stationary point, so we're going to set this equal to 0. Now we're going to add that 8 over 3x to both sides, and then divide by 8 over 3. So we'll end up with x equals 15. So we know that there is a stationary point at x equals 15, but we do have to double check that it's a stationary point. So let's just draw up a table down here. So we need that 15, and we need a point on either side. So maybe let's pick 10 and 20. It could have been just 14 and 16, it doesn't matter. So we know it's a stationary point here. If we substitute 10 into the derivative here, we would end up with 40 over 3, which is a positive value. And if we substitute in 20, we'd end up with minus 40 over 3, which is a negative value. So this has clarified that it is definitely a maximum that we're looking at. So we've got our x coordinate, but we do need our x value. We do need our y value as well. So to find our y value, there's a couple of places we could substitute it in, but probably the easiest is in here because we've already got y as the subject. So we would have 40 minus 4 over 3 times 15, which would give us 20. So we know that the maximum area is going to occur with dimensions 15 metres by 20 metres, but the question's asked us to find what the possible maximum area is. So our area would be equal to 15 times 20, which would give us 300 meters squared. So our maximum possible area is 300 meters squared for this problem.